So hello everyone. Welcome to another episode of Deep Dive Knowledge Talk. Hello everyone. Tonight we dive into how LLMs enhance reasoning with step-by-step thinking, like a recipe. Really well explore COT limitations, search generalization hurdles, and how self-improvement and feedback improve adaptability, considering inherent LLM reasoning and future paths. Can you explain how the ability of large language models, LLMs, to generate intermediate steps or tokens enhances their whole reasoning capabilities when solving complex problems?
Large language models, LLMs, can be thought of like a chef preparing like a complex dish. Instead of just throwing all the ingredients into a pot and just hoping for the best, the chef follows a recipe, step by step, measuring and mixing ingredients along the way. This is similar to how LLMs generate intermediate steps or tokens when solving complex problems. So, when an LLM encounters a problem, it can break it down into smaller, manageable steps, just like the chef follows each part of the recipe. By generating these intermediate tokens, the model can clarify its reasoning and make adjustments if needed, ensuring that it just stays on the right track. So this process helps the model arrive at the correct final answer more effectively, and if the model were to just jump straight to the final answer without these intermediate steps, it would be like the chef trying to serve a dish without following the recipe. This could lead to mistakes or even just a dish that isn't edible at all. In essence, generating intermediate tokens enhances the whole reasoning capabilities of LLMs by providing a structured approach to problem solving, making them more reliable and accurate in their responses.
What are some specific challenges associated with using chain of thought, COT prompting LLMs, and how does it differ from methods like Supervised Finetuning or Reinforced Finetuning
Using chain of thought, COT, prompting in large language models, LLMs, is basically like trying to teach a child how to solve a puzzle by asking them to think out loud. So, while this method can sometimes help, it also comes with specific challenges. One challenge is that COT prompting often requires task-specific examples. So, imagine if you had to teach a child how to solve a different puzzle each time, but you only had a general instruction, like think step by step. So this approach might not work as well as showing them just a few similar puzzles first. As a result, so while COT prompting can be simple and effective in some cases, it typically performs worse than methods that provide specific examples. In contrast, supervised Finetuning SOT is more like giving a whole child a complete guidebook with detailed instructions on how to solve various puzzles. In the SFT, the model learns from a collection of problems and their step-by-step solutions, provided by human annotators. This method aims to maximize the likelihood of getting the right answers, making it more structured and focused. So, Reinforced Finetuning, on the other hand, is like giving the child feedback after they try to solve a puzzle. Like, if they make a mistake, so you guide them on how to improve. This method helps the model generalize well for tasks that can be automatically verified, but it may not work as effectively for tasks that don't actually have clear right or wrong answers. In summary, while COT prompting encourages thinking through problems step by step, it really can struggle without specific examples. So in contrast, SFT and Reinforced Finetuning provide more structured and guided approaches, helping the model learn and improve more effectively.
Could you elaborate on the limitations of supervised Finetuning SFT in terms of generalization, and how methods like self-improvement and Reinforced Finetuning are designed to address these issues? So,
Supervised Finetuning SFT can be compared to a student learning from a textbook. While the textbook provides a lot of information, the student may struggle to apply that knowledge in new situations. In the case of SFT, the model learns from a set of problems and their step-by-step solutions, but it doesn't always generalize well to different or unseen problems. So this limitation means that even if the model has learned specific solutions, it may not be able to adapt that knowledge to solve new challenges effectively. Additionally, scaling the thought process, like trying to cram more information into the same textbook, doesn't necessarily improve the model's ability to just generalize. It might just lead to more of the same type of information without expanding the model's understanding. To address these generalization issues, so methods like self-improvement and Reinforced Finetuning come into play. Self-improvement is like a student practicing by solving problems on their own and then checking their answers against a solution guide, like in this method. The model generates its own problems and solutions, allowing it to learn from its mistakes and improve over time. So this process helps the model become more adaptable and better at handling a wider variety of problems. Reinforced fine-tuning works similarly, but with a focus on feedback. Just imagine a student receiving grades and comments on their homework. In this method, the model not only learns from correct solutions, but also minimizes the likelihood of making mistakes. Just by continually refining its understanding based on feedback, the model can improve its performance on tasks, especially those that can be verified automatically. In summary, while SFT has just limitations in generalization, so methods like self-improvement and reinforced Finetuning help the model learn and adapt more effectively, allowing it to tackle a broader range of problems with greater accuracy.
How do the concepts of just self-improvement and reinforced fine-tuning contribute to the overall effectiveness of LLMs in reasoning tasks? And what potential advantages do they have over traditional fine-tuning methods?
Self-improvement and reinforced fine-tuning are like training, like a sports team, to become better at their game. Instead of just practicing the same plays over and over, the team learns from each game they play, analyzing what worked and what didn't. So this approach can significantly enhance the overall effectiveness of large language models, LLMs, in reasoning tasks. Like self-improvement allows the model to generate its own problems and solutions, similar to a player creating new strategies based on their experiences. By doing this, the model can learn from its mistakes and successes, just continually refining its understanding and improving its reasoning ability. This process helps the model adapt to new challenges and broaden its skill set. So reinforced fine-tuning adds another layer by providing feedback on the model's performance, much like a coach giving players tips after watching them play. So this method really focuses on maximizing correct solutions while minimizing errors. By receiving feedback and adjusting its approach, the model becomes more adept at handling a whole variety of tasks, especially those that can be verified automatically. The potential advantages of these methods over traditional fine-tuning, like supervised fine-tuning SFT, are significant. While SFT relies on a sort of fixed set of problems and solutions provided by humans, which can limit generalization, self-improvement, and reinforced fine-tuning, enable the model to learn and evolve based on its own set of experiences. So this adaptability leads to improved performance in reasoning tasks and allows the model to tackle a wider range of challenges with greater accuracy. In summary, self-improvement and reinforced fine-tuning contribute to the effectiveness of LLMs by fostering continuous learning and adaptation, providing feedback and enhancing the model's reasoning capabilities beyond what traditional fine-tuning methods can actually achieve.
What are the implications of leveraging the inherent reasoning capabilities of pre-trained LLMs without explicit prompting or fine-tuning? And how does this challenge existing assumptions about the need for additional training methods,
Leveraging the inherent reasoning capabilities of pre-trained large language models like LLMs without explicit prompting or fine-tuning is like discovering that a well-trained athlete can perform well in a game without needing constant coaching. So this realization has really important implications for how we view the capabilities of these models. First, it suggests that LLMs possess a level of reasoning that can actually emerge naturally from their training on vast amounts of text data. This means that they can generate coherent and logical responses based on their understanding of language and context, so even without additional specific training or prompts. This challenges the existing assumption that models always need fine-tuning or specific prompts to perform well in reasoning tasks. Moreover, this ability to reason inherently implies that LLMs can be more flexible and adaptable in real-world applications. If they can actually utilize their built-in reasoning skills effectively, we might not need to rely on extensive additional training methods for every new task or problem. So this could lead to more efficient use of resources and quicker deployment of LLMs in various applications. However, it also raises questions about the limitations of these models. While they can reason well, in many contexts, there are still tasks that may not just be automatically verifiable. This means that while the models show promise, they might not always reach the same level of accuracy or reliability as those kind of trained specifically for certain tasks. In summary, recognizing the inherent reasoning capabilities of pre-trained LLMs without explicit prompting or fine-tuning challenges, like traditional views on the necessity of additional training method. It opens up possibilities for more efficient applications while also highlighting the need to really understand the boundaries of what these models can achieve on their own.
So how might future research build upon the findings regarding chain of thought, decoding self-improvement, and reinforced fine-tuning to further enhance the reasoning capabilities of large language models?
Future research can actually build upon the findings regarding chain of thought, decoding, self-improvement, and reinforced Finetuning to enhance the reasoning capabilities of large language models, little ones in several ways, much like a coach, refining a team strategy based on past performance. One potential avenue is to further explore and refine chain of thought, like decoding. Researchers could actually investigate how different types of prompts can elicit even more effective reasoning processes from LLMs. By experimenting with various prompting techniques, they may discover ways to make the models more adept at breaking down complex problems into manageable steps, so leading to clearer and more accurate answers. Additionally, the self-improvement method can be so expanded. Researchers could focus on creating more sophisticated mechanisms for the model to generate and evaluate its own kind of problems and solution. This might involve developing advanced algorithms that allow the model to learn from a wider range of experiences, thereby enhancing its adaptability and problem-solving skills. Reinforced fine-tuning could also be further optimized. Researchers might explore ways to create feedback loops that actually provide more nuanced evaluations of the model's performance. By incorporating feedback not just on correct or incorrect answers, but also on the reasoning process itself, so models could learn to refine their thought processes and improve their overall reasoning capabilities. So, moreover, combining these approaches could lead to breakthroughs like, for instance, integrating self-improvement with code decoding might allow models to generate reasoning steps that are not only correct but also more innovative or diverse, So this could enhance their ability to tackle unique problems that go beyond standard benchmark. Lastly, research could focus on aggregation and retrieval techniques. By developing methods to combine multiple reasoning outputs or retrieve relevant information from vast data sets, models could really improve their accuracy and depth of understanding, leading to more robust reasoning ability. So in summary, future research can enhance LLM reasoning capabilities by refining prompting techniques, expanding self-improvement mechanisms, optimizing feedback and reinforced Finetuning, and integrating these methods to create more powerful and adaptable models.
So, thank you for joining us today. So it's been an incredibly insightful discussion with our esteemed researcher. We've explored how large language models are becoming more adept at complex reasoning, much like a seasoned chef, meticulously following a recipe, by generating those crucial intermediate steps, so these models significantly reduce errors and arrive at more precise solution. However, we also learned about the intricacies of chain of thought, so prompting noting its reliance on specific examples can sometimes limit its effectiveness compared to more guided approaches like supervised Finetuning and the adaptive nature of reinforced Finetuning. A key takeaway was the challenge of generalization with supervised Finetuning, how a model might excel at a specific task, but really struggle when faced with novel problems. So this led us to discuss promising avenues such as self-improvement, where models learn through independent practice, and the power of reinforced fine-tuning, which refines their understanding through continuous feedback. Intriguingly, we touched upon the idea that pre-trained models might possess a remarkable level of inherent reasoning, perhaps challenging the assumption that so extensive additional training is always necessary. Looking ahead, the path is pretty clear for future advancements, refining our prompting techniques, bolstering self-improvement mechanisms, optimizing those vital feedback loops, and potentially combining these powerful approaches to unlock even greater reasoning capabilities in these remarkable models. A huge thank you once again to our guest for sharing such profound insights, and just to all of you for tuning in. So we look forward to seeing you next time.